I suppose that everybody feels hungry, so I have to terminate as soon as possible. Okay, anyhow, here I show you the colleagues of my groups. So Dr. Matsui and Dr. Seki, they are main players on what I'd like to present today. And we also collaborate with Professor Fujimori for measuring the X-ray MCD, and the Professor Ito for Osaka University, and Professor Harima. And also we are collaborating with Professor Yatsi and Otsu for measuring the dynamic photoluminescence systems. Okay. So here I'd like to show you the contents of my talk. First of all, I'd like to briefly introduce you what we're interested in, the background of our research. And then I'd like to discuss about the coupling characters between the electron spin, so-called spin electronics. And finally, I'm going to the discussion of coupling between the carriers, excitons, and plasmons. Okay. So our group are mainly focusing on the oxide semiconductors. Here I show you the table of the physical properties of various kinds of wide gap semiconductors. As you can see, the zinc oxide has unique characters compared with other kinds of materials. For example, it has relatively small dielectric constant and a very small exciting Bohr radius. And it must be noted that the exciting binding energy is very huge. So you can remember that the room temperature sound vibration energy is at 25 milli-electron volt. It's good information, good news for us to operate such a exciting related to the phenomena at the room temperatures. And the zinc oxide itself is very old materials so far. For example, very old areas, so it was used as a pigment of the white paint. And nowadays also was widely used as a surface acoustic wave, so piezoelectric devices. And the fluorescent materials also available, always combined with the zinc oxide. And in these days, so it shows the various kinds of the functional characters, such as a transparent filter transistor is available by using zinc oxide, and the transparent electrode widely used for the solar cell combined with the silicon or other organic solar cell materials. And today I'd like to focus on the magnetic characters of zinc oxide materials. So anyhow, by overviewing these functions, it can be said that the environmental friendly and human body friendly materials, it is good as a green IT, so technology, information technologies. Okay. So first I'd like to discuss the how to control the good quality crystal growth, such as to demonstrate the quantum wells and quantum dot structures. So our group operate as a laser MP system, laser molecular beam epitaxy systems, I'm showing here. And in this system, the laser beam is focused on the ultra vacuum chambers. So at the center of this chamber, the target, such as zinc oxide or as a compound, are set and focus on it, and they evaporate as a species and deposit the film on the opposite side of the substrate. And in our experiment, we use various kinds of substrates such as the strontium titanate, sapphire, and zinc oxide single crystals. Nowadays, we can easily, so commercially available zinc oxide single crystals. It has a very high quality. And anyhow, so for depositing zinc oxide, we treat these kinds of substrate by using the O2, also high temperature needing the treatment, and of course the chemical operations also to make atomically smooth surface and deposit the film on these kinds of substrate. And zinc oxide has oxide crystal structures, and it shows the various very interesting crystallographical behaviors. For example, when we select the O polar surface, here's O polar, and the backside is the zinc polar, plus plane and minus plane. And in case of the all polar surfaces, the zinc oxide film itself shows these kinds of the screw-like, the hexagonal shapes, so due to these crystal structures. And in case of the zinc polar surface, on the other hand, it shows the two-dimensional so film growth. It is easily available to make quantum wells by using these zinc polar surfaces. And the more interesting is that when you select the M polar means the non-polar surfaces, 1, 0, 1, bar 0, this shape. It shows a very unique one-dimensional nano or wires structures. So it is also very interesting for fabricating the quantum wires structures and also. But anyhow, today I'd like to focus these all polar or zinc polar surfaces. And then, fortunately, zinc oxide also has various kinds of families, such as the cadmium oxide and magnesium oxide. Here is the zinc oxide, and band gap, and the lattice parameter A. So, with combining with the magnesium, that means that with the replacement of the magnesium, the band gap can be expanded to the 4.5 and at most 7 eV. And when we replace the cadmium, so I think oxide zinc by cadmium, the band gap will shrink like this. So that we can easily control the band gap alignment, and without any changing the lattice parameters. Here's good information for making heterostructures and the quantum wave structures, comparing with that of the gallium nitride. In this case, it shows a very large lattice mismatch in this case. But in this case, so they are the ionic binding materials, therefore it has a very tolerance to fabricate these kinds of heterostructures. And then at first we confirmed that the topmost threshold to form the coherence growth, and the change to the deep coherence. It means having a second or something like that. Then up to the several tens nanometers, so it shows the very coherent crystal structures, and it fixed the lattice parameter. Here is the reciprocal lattice mapping patterns, so you can observe the pattern from the zinc oxide single crystal and the films like this. So locked in the in-plane characters like this. And up to the several tens nanometers, we can get the coherence growth. And in summary like this, with changing the lattice thickness of the films, or in the case of the magnesium, 3.7%, 37% placement. So around here is the threshold to changing the growth mode. So following by the very well-known the experimental Matthias theories model, we can estimate that the critical thickness is around the 50 nanometers in case of the zinc oxide and the magnesium zinc oxide in this composition. But anyhow, we check such conditions and how to get the two-dimensional growth and to get these kinds of quantum dot structures. And again, I showed you the AFM pictures of these kinds of various kinds of the same period, thickness of the magnesium replaced zinc oxide, and at the relatively low thin layers, it shows the two-dimensional natures. It shows a coherence growth, and above such a threshold thickness, it shows these kinds of quantum dot structures. Therefore, when we like to form the quantum wells, quantum single well, multi quantum wells, we have to set the composition and the thickness as around these growths. And of course, when we like to form the quantum dot structures, so we set the conditions around showing here. And I'd like to show the magnetic characters of these materials. So when we started on these kinds of experiment about 10 years ago, several theoretical papers suggested that the ferromagneticity of these materials, for example, in case of it suggests that the only is zinc oxide and gallium nitride the good candidate for showing the room temperature ferromagnet. If we like to, we can introduce the enough carrier concentration and the sort of the composition of the magnetic ions. But, strictly speaking, it is so not fit for our experiment because in our case, so N-type semiconductor. But anyhow, so this paper encouraged us to jump into this kind of research field. And also, Professor Yoshida's group suggested that the cobalt is one of the good candidates for generating the magnetic characters, ferromagnetic characters, in case of the zinc oxide. And in addition, so from the theoretical calculation suggested that it must show half metallic materials. It is also good for when we make it the application. So realistic devices, the half metallic spin materials is a good candidate for good performances. And so we reported the ferromagneticity of the cobalt of zinc oxide for the first time, and here shows the hysteresis characters measuring by the squid, so magnetic susceptibility, such that the ferromagneticity. And we also confirmed that the ferromagnetic characters by using the magnetic circular dichroism, and we also confirmed that using the anomal hole effect transport behaviors and the magneto-optical behaviors suggests that the ferromagneticity occurs in these kinds of the materials. And so we'd like to control the ferromagneticity by controlling the carrier concentrations. So here is the carrier concentration dependent of the magnetization. So as you can see, in the case of the relatively low carrier concentration, for example, 10 to 17, so less than 10 to 18, so it shows almost the paramagnetic characters. But if we can introduce enough carriers, so for example, up to the 10 to 19, so it shows this kind of large magnetic natures. So here, again, I show you the carrier concentration dependent of the magnetization. This line shows the cobalt substituted zinc oxide, zinc cobalt alloy layers formed on the here's the zinc polarity character substrate, and this line shows the magnetization of the films formed on the all polarity characters. But both of them shows these kinds of the carrier concentration dependence on magnetization. With increasing the carrier concentration, the total value of the magnetization increase like this, and above the sort of the density, motor density, like the 6 multiplies 10 to 18, it shows the almost 2 mu b per cobalt. It's enough large to say that it is ferromagnet. And when we observe these kinds of carrier concentration and the mobility of the also activation energy by changing the carrier concentration, it shows the two kinds of the activation energy. That is, in case of the relatively large carrier concentration, the activation energy is very small, which means that the shallow donor is good. Here is the very small activation energy. The shallow donor suggests the enhance the carrier migration, and eventually shows the ferromagneticity occurs. In case of the relatively low carrier concentration, the deep donor is it's intrinsic, or it is not enough to migrate each other. It shows the paramagnetic natures in these materials. So roughly we can say that these band structures will be available. And we also confirmed that the spin natures of these materials collaborated with Professor Fujimori by using the X-ray MCD, magnetic circular dichroism, using the synchrotron radiation, and by analyzing these kinds of data. So this magnetic value comes from mainly from the spin natures. Most part of the magnetic characters comes from spins. In this case, the total model not so large anyhow. The total is 3.5 μb, but the 0.24 μb comes from the spin, and the orbit comes from 0.067. And as one of the demonstrations, we formed these kinds of method structures for demonstrating the magnetic tunnel junctions, like these structures. And in this case, the insulating layer, barrier layer, is, for example, magnesium oxide or sapphire. So one of the typical data shows that here is the cobalt doped zinc oxide and sapphire layers and the iron. This tri-layer shows these kinds of the hysteresis natures. So actually it is not enough values, but anyhow it can demonstrate, at least it demonstrates that the memory characters by using these kinds of the difference of the coarse magnetic field of these materials. And when we change the cobalt concentration, it shows a unique magneto resistance characters. Here is the magnetic transport natures depending on the applied magnetic field. So in the non-doped, so pure zinc oxide, it shows this kinds of the negative MR effect. So, but in case of the cobalt doped from 0.15 to up to the 2%, so with increasing the cobalt concentration, the turnover, so magnetic field also shift to the lower magnetic field like this. And in this case of the, for example, our sample, so at very low temperatures, it shows these kinds of the carrier concentration dependence of p-value. P-value means spin polarization ratios estimated. So some more causing bias at this model. But anyhow, so there is some relation between such spin characters and the conducting behaviors are demonstrated in these systems. So this is one of the example of the interactions. Okay, so by using these kinds of the materials, one knows the practical application we would like to fabricate is this kinds of the MTG junction, magnetic tunneling junction, and the field defect transistors like this. But the other interesting field is that the spin phonon interaction, these regions. So to do so, we have measured the magnetic, dependent of such optical characters of these materials. So here is the absorbance spectrum of the bandage structures of the zinc oxide. So for example, in case of the non-doped zinc oxide, it shows a very sharp, free excitant, absorbance characters like this. And with adding the cobalt concentration up to the 5%, it shows the such a smearing is band tailing at the band edge absorbance characters. And we also measure that the photoluminescence characters in the same conditions, and the cobalt concentration dependent on the peak position energies, shows the almost consistent characters, both in the absorbance, band edge absorbance, and the photoluminescence from such extended band existence. And anyhow, but one of the interesting point is that the intensity of the photoluminescence dropped rapidly, dramatically with increasing the cobalt concentration. It is not of course it is interesting, but it is not good for example, practical application to such a magnetic semiconducting characters applied to the optical characters. But anyhow, I'd like to confirm what's happened in these materials when we applying the magnetic field. So we measure the two energy state. One is around the 1.8 electron volt. This energy band is due to due to the intra-emission of cobalt 3D, DDE, so transfer energy levels. So at the peak position and the intensity shown here, the intensity decrease with increasing the magnetic field, and also the position shows the shift to the blue regions with increasing magnetic field. Here I put the magnetic field dependence of the zero boson line peak. So intensity and the position. So up to around the 3 Tesla is the threshold magnetic field. So it shows almost constant character, but above the threshold magnetic field, so intensity drops rapidly, and also the peak position shifts towards the blue regions. And this is the schematic models of the here is the band edge emissions, and here is the DD emissions. So therefore, there may maybe some radiation transfer, so energy transfers from the band edge emission to the DD band emissions. But to confirm it, we also observe the photoluminescent characters at the band emission energy regions. And here is the photoluminescence characters, non-doped, so pure zinc oxide, and the cobalt doped zinc oxide like this. In the case of the pure zinc oxide, also as you can imagine that there is no difference with even if we apply the large magnetic field up to the 7 Tesla, there is no difference. But in case of cobalt doped, so magnetic, zinc oxide, zinc cobalt oxide, it shows the shoulder peaks. Here is FA is a free existent and D is a bound existent, and we just neighbor the bound existence as a new luminescence characters occurs to the relatively large magnetic field. So ICO, we shown that like this, and so here is the intensity, photoluminescence intensity of the ICO peaks, and comparing with the former such an emission from the cobalt, so the 1.88, so like this. So it shows the opposite behaviors like this. So after the 3 Teslas, there is no peaks, shoulder peaks at the bound emission energy regions, but above the threshold, peak increase like this, and on the contrary, the emission at the cobalt, so the state is suppressed like this. It means that there is some energy transfers from the band emission to the DD band. And so actually is energy, density states of the cobalt, charge transfer level is located just below the conduction band of the zinc oxide for S levels, like this. So detail, I'm not sure, going to the details, but anyhow, some of the energy state located here, and such a demonstrating, with under the large magnetic field, overlapped to this energy state, and eventually it shows them there is some transfer characters, from the cobalt characters. And so far, for example, when we like to apply the spin photonics like this, so Professor Ono of University demonstrated that the pioneer works, for example, by using these kinds of the PN junctions, we can read out the spin information through the light information. And then we'd like to expand these kinds of the possibilities. And to do so, one of the interesting field is surface plasmon phenomena, for example. And so one of the typical, for example, model, samples of our devices is that first we fabricate these kinds of quantum single wave structures, and the light irradiate from here, and we deposit the metallic, for example, or dot or metallic lines showing here, and combining with this quantum wave and the metallic patterns, so we can read out these kinds of the magnetic light information through the such as plasmon informations. And as you know, the surface plasmon is widely used, widely distributed in these days. So, for example, the solar cell, in the field of the solar cell is one of the good candidates for applying the plasmon natures to enhance the quantum efficiency. And also the standard surface plasmon resonance devices will be used for the biosensors. Therefore, we'd like to combine these kinds of the materials to make new kinds of the devices, photonic devices. So to do so, also one thing we have to do is that the having a crossing point of the light line of the bright line of the, for example, air and metal curves and the semiconductors, zinc oxide curves. Unfortunately, zinc oxide has a very small Bohr radius. Therefore, we can separate very small sizes enough to accumulate the information. But anyhow, so to do so, again we show the such a phase diagram. Lattice parameter constant dependent on the band gap. In case of the originally pure zinc oxide, it has a 3.3 ultraviolet blue lesions. Therefore, there is no relation between, for example, again I showed to pick up the information of the surface plasmon of the silver and the zinc oxide, it line is showing here. But the pure zinc oxide light line is showing here. But we have to suppress and decrease the band gap down to the 2.77 or 2.8 electron volt regions. To do that, we have to make cadmium doped zinc oxide systems. And unfortunately, we successfully found that the band edge controls by controlling the concentration of the cadmium ions. So here is the pure zinc oxide, and with increasing the cadmium concentration, the luminescence, so band edge, here is the photoluminescence, but the band edge comes down to the 2.7. Right here, there is a crossing point. It means that this information can be read out by using these devices. And to fabricate the surface plasmon devices, we have to optimize the size. Size means the separation length. Here is the single quantum wave structures are formed on the zinc oxide buffer layers, and the separating layer, on the top of the separating layers, we deposit the silver. And we estimate the, for example, decay length of the, with changing the separation or length. So up to the 10 nanometers, so intensity of the coupling is not so small, but above the 30 nanometers, it's too thick to coupling it. Therefore, we have to keep the separation length is less than 10 nanometers. And then we also confirm that the optimum quantum wave width in case of the single quantum waves with changing the wave lengths, and we can tune the photon energies around the 2.8 eV. Therefore, from this result, we show that the single quantum wave structures having the wave width of the 4.8 nanometers, tuning the energy, plasmon energy is 2.8. And here's cross-sectional TM view graph of the single quantum waves capping the zinc oxide like this. It shows the smooth surfaces, and on the top of the capping layers, we fabricate the silver metals to measure the plasmon characters. And then we fabricated two kinds of the silver layers. And one is a very smooth silver thin films, two-dimensional thin films, and the other is the dotted, naturally, self-assembled dotted silver patterns. So in case of the very flat surfaces, there is, for example, here is the photoluminescences with and without silver layers. Of course, the intensity, total intensity decreases a little bit, but the luminescence character can easily observed in these systems. But in case of the dotted silver patterns. On the contrary, such a luminescence from the quantum well structures or suppressed. So it shows that the large inhibition occurred in case of such a dotted pattern. It suggests that the such energy transferred from the quantum wells to the silver like this. Okay, and at first we confirmed that the such luminescence natures in case of these cadmium zinc oxide. This is without silver topmost layers, but there are two different mechanisms, so decay mechanism. Here is the temperature time dependence of the decay curves. In the case of the short decay, this line, and the relatively long lifetime decay length like this. In the short decay suggests that the combination of the exciton in the inside these materials and the long lifetime region, yes, like this long time region suggests that the such a trap to the ionized state or the hopping to the ionized state. There is two different types. The importance is this one, and we fabricate the silver dotted patterns on these single quantum wells, and so temperature dependent of such dynamic luminescence phenomena. In the case of the relatively high temperatures, so there is no difference between the with and without silver layers, topmost layers. But in case of the low temperature, on the other hand, so when the sample covered with the silver, it shows the very long time, so long lifetime, it can be observed. It suggests that such information from this light information from the quantum well layers to transfer to the silver layers. Indeed, so we cannot say that anymore, but anyhow, we estimated that the energy transfer rate, K energy transfer rate, or combined, related with such lifetime characters. So here is the K non-radiative natures, and here is the K radiative layers. Our experimental results of the K energy transfers almost similar characters up to the temperatures of the 90 kelvins. So this experimentally suggests that such a threshold temperature observed for the first time, and such radiative recombination regions occurs as the energy transfers from the quantum well to the subplasmon mode, and it's threshold temperature is the 90 kelvins. So this temperature, threshold temperature, strongly depends on the quality of the, for example, doping characters of the zinc oxide natures. And we demonstrated that for example, space distance dependence of the quantum efficiency values, up to the 200 very thick regions there is no relation, but the relatively small relation. This quantum wave, exciting information from the quantum waves combined with the metallic topmost layer. Therefore, this side is good for making such a spin plasmon devices in case of the cadmium doped zinc oxide. And finally, I show you one of the local surface plasmon characters of this one of the typical materials. For example, in case of the luminescence natures, it actually shows the quantum well peaks from these observing around the cadmium bandage characters, cadmium zinc oxide bandage characters, and so when we inform the silver dotted patterns on that, it's the absorbance actually so the plasmon absorbance characters actually located around the natures. Okay, I have to terminate my talk. So today I'd like to explain about the relation of the electron and spins, that is spin electronics based on the cobalt zinc oxide, and also we have introduced that such a possibility of the spin light interactions in the case of the some plasmon also based zinc oxide devices. Okay, thank you very much for your attention.